Solar time is measured by intervals between two consecutive passes of the sun. However, true solar days vary due to axial tilt and uneven orbital motion. The difference between mean and true solar time is called equation of time. Understanding these nuances allows us to sync our life rhythms with the universe.
It's a common assumption that the most fundamental way to measure time is by simply observing the sun. After all, what could be more natural? The sun rises, it reaches its highest point, it sets. It seems like the perfect clock. Well, the reality is far more complex. The sun, as it turns out, is a surprisingly inconstant timekeeper. Today, we're going to deconstruct this celestial clockwork and explore why the time on a sundial and the time on your watch are almost never in agreement.
So here's the path we'll follow. We're going to begin with the most intuitive concept, true solar time. Then we'll investigate the fundamental flaws in that system. From there, we'll introduce the elegant, idealized solution that humanity engineered, mean solar time, and explore how we synchronize these two realities. Finally, we'll discuss why this entire framework is absolutely essential to our modern world.
All right, let's begin with the original clock, the one that has governed human activity for millennia, the sun itself. This is the basis of what astronomers call true solar time.
So, what exactly is a true solar day? Well, imagine a great circle in the sky, an invisible line that runs from the north celestial pole through the point directly over your head, the zenith, and down to the south celestial pole. This is your local meridian. When the center of the sun crosses this line at its highest point, we call that upper culmination, or more simply, true noon. A true solar day is just the precise interval it takes for the sun to return to that exact same highest point on the next day.
This concept is formalized in a rather elegant equation. True solar time can be calculated from the sun's hour angle. That's its angular distance west of your local meridian. You see, at true noon, the sun is on the meridian, so its hour angle is 0. The formula then gives us exactly 12 hours. As the Earth turns and the sun appears to move westward, its hour angle increases, and this equation directly translates that celestial position into the time you'd read on a sundial.
However, this is where the perceived simplicity of our solar clock begins to break down. You would intuitively think that the length of a day is constant, but when measured by the real sun, it is not. This natural clock is remarkably unstable, and now we will examine precisely why.
This instability doesn't just come from one source. It actually arises from the confluence of two completely separate astronomical phenomena, both happening at the same time. Let's look at each one in turn.
The first reason is the obliquity of the ecliptic, or more simply, Earth's axial tilt. Visualize Earth's equator projected outward onto the celestial sphere. This creates a line called the celestial equator. Now, the sun does not travel along this line. Its apparent path, the ecliptic, is tilted relative to the equator by about 23.5 degrees. This tilt is what gives us seasons, but it also fundamentally distorts our measurement of a day.
And here's the consequence of that tilt. Near the solstices in June and December, the sun's path on the ecliptic runs nearly parallel to the celestial equator, so a segment of its motion projects as a relatively long distance onto the equator. But near the equinoxes in March and September, its path cuts across the equator at a steep angle. This means the very same distance traveled along the ecliptic projects as a much shorter segment onto the equator. Since the length of the day depends on this projected motion, the day itself appears to change in length.
The second contributing factor is the eccentricity of Earth's orbit. Our planet's path around the sun is not a perfect circle, but a slight ellipse. And according to Kepler's second law of planetary motion, this means the Earth's orbital speed varies. We move fastest when we're closest to the sun, at perihelion in early January, and slowest when we're farthest away, at aphelion in early July. From our perspective on Earth, this makes the sun's apparent speed against the background stars change throughout the year. So, what happens when we combine these two effects, the axial tilt and the elliptical orbit? Well, you get significant variation. A true solar day around December 22nd is about 51 seconds longer than a true solar day around September 23rd. Now, 51 seconds might not sound like much, but for any society that requires precision and coordination, a clock that gains or loses almost a minute from one season to the next is simply unworkable. To resolve this issue of non-uniformity, astronomers and horologists devised a brilliant and elegant solution. They essentially invented a new clock. an idealized, theoretical timekeeper that runs with perfect consistency. This is really the heart of the solution. We replace the physical, observable true sun with its variable speed and tilted path with a fictitious object. We call it the mean equatorial sun. Now, this imaginary sun has two very important idealized properties. First, its path is not the ecliptic. It moves along the perfectly flat celestial equator. And second, its speed is not variable. It moves at a perfectly uniform rate equal to the average speed of the true sun over an entire year.
And by using this idealized mean sun, we can finally define a mean solar day. It's the interval between two successive culminations of this fictitious object. Because its speed is, by definition, constant, the length of a mean solar day is also constant. This is the 24-hour day that all of our civil clocks are based on. Okay, so we now have two distinct time systems operating simultaneously. The true solar time dictated by the actual sun, and the mean solar time dictated by our idealized theoretical sun. The crucial question then becomes, how do we relate the two? This is accomplished by what is known as the equation of time.
The equation itself is wonderfully simple. It defines the equation of time, represented by the Greek letter eta, as the difference between mean solar time, that's clock time, and true solar time, sundial time. You can think of it as the correction factor, the precise number of minutes you would need to add to or subtract from a sundial beating to get the time on your watch.
Now, the final value of this equation is not a simple sine wave. It's actually a superposition of two separate waves. The first component, driven by the eccentricity of our orbit, has a period of 1 year. The second component, caused by the axial tilt, has a period of half a year. When you mathematically add these two distinct waves together, you get the more complex, asymmetrical curve that represents the equation of time.
And here are the concrete results of that complex curve. You can see there are only 4 days in an entire year when the equation of time is 0, days when a sundial and a perfect clock would agree. But look at the extremes. Around February 11th, a clock is running more than 14 minutes ahead of the sun. And around November 2nd, that same clock is more than 16 minutes behind the sun. That's a total swing of over 30 minutes throughout the year.
Now, this might all seem like a purely academic distinction, but the practical importance of creating mean solar time cannot be overstated. This abstraction is a cornerstone of modern technological civilization. Just think about it. Everything from global navigation systems like GPS to the scheduling of trains and flights to synchronized scientific experiments relies on a globally accepted, uniform, and stable standard of time. A society built on this level of precision simply cannot function using a clock that's inherently variable. In essence, we have made a deliberate choice to prioritize mathematical consistency over direct natural observation. And this brings us to a rather profound final thought. The time that governs our lives, the time on our phones, our computers, our watches, is not a direct measurement of a natural phenomenon. It is an ideal, a human construct designed for order and predictability. So I'll leave you with this question. What does this choice reveal about us? Is it a testament to a fundamental human quest for order in a chaotic universe? Or does it signal a growing, perhaps necessary, detachment from the natural rhythms of the cosmos itself?
Thank you, friends. Strive for understanding and become wiser. See you soon.